Good afternoon, ladies and gentlemen. My topic is the radiation assurance test in BMTI. Here we will give the outline. First, I will give a brief introduction for BMTI, and then we'll talking about using BMBIST structure for SEE test. And then I will talking about the SEE failure analysis with laser. Finally, I will talking about the test method for distinguishing SEU and SET, also for some SET analysis. First, I will give the brief introduction for the BMTI. I think BMTI is a Chinese leading organization in radiation hardness microelectronics research. Also, the institute is the largest radiation hardness IC provider in China. The main achievements include several high reliability RHIC design platforms and completely RHIC product family. Also, we have advanced package testing and 4-inch fab line. Here is the design platform. Now we have 1 micron, 0.5 micron, and also a 0.18 micron design platform. This is a Metro 3 platform. Now we are developing the 65 nanometer. Next step, we will develop the 28 nanometer design platform. Here is the IC product family. We deliver like AD, CPU, and FPGA, also some memory, also the bus driver, and something like this. Now I think we can deliver more than 200 kind of IC products. Also, we are working on packaging, testing, and fab line. We have a ceramic package line up to 1,005 pins, different kind of package structure like BGA, QFP, something like this. And also we do some MCM and 3D package. For the testing line, there are up to 1,000 test channel, and we can do the FPGA, SoC, RF, ADC, DAC, and memory chip testing. For the reliability, we do the screen, or actually we can say that we can deliver the one station for package testing and reliability. For the fab line, we only have a 0.8 4-inch fab line. Mainly work for the radiation-hard diode, transistor, and VDMOS, like FRD. And also we're working for the MEMS. So this is not a mass production fab line. They can deliver 3,000 wafer per month. So it's not a very big fab line. Next, we are talking about using BMBIST structure for SEE test. For a complex IC, it's very difficult to develop. It's very difficult to evaluate and define the SEE hardness by limited function tests. So in my institute, we want to do a simple method. It can find a method to test the West case. BIST is popular for IC testing. So we use the scan chain and memory BIST to evaluate the SEE performance. Almost 100% of the sensitivity module in IC can be covered by BIST test. Here we give some result for the testing. We can find here, okay. We can find the sigma BIST is always greater than the sigma function. So SEE test with BIST is the worst case test. So here is we can see the figure on the left. So we think the BIST test result can be a conservative estimation of any function test result. But when we do this, we have to know what's the effective fluence in SEE test, especially with the MBIST. Here is some very detail for how to calculate the effective fluence. Depends on the arithmetic. They will give a different effective fluence. But anyway, by considering the effective fluence, SEE test with the MBIST can accurately evaluate the SEU performance of the embedded memory. The third one I will talking about the SEE failure analysis with the laser. Pulse laser is a good tool to estimate SEE performance of integrated circuits. In BMTI, we mainly take advantage of the laser for positioning of SEE error or failure. Next, I will give two examples. One is the SEE sensitive load, how to positioning the sensitive load in the SEU hardening SRAM. Use the heavy ion test shells for 0.18 micron convention dice. The LET is about 37 MBU. For 65 nanometers conventional dice, the LET is less than 14 MBU. Here is the laser result. 3 areas in a bit cell is sensitive to SEU, was found by the laser test. Also, we do the simulation here. So according to the laser result, TCAD simulation gave the reason for the sensitivity. One is the charge sharing between the NMOS, and the other is the charge sharing between the NMOS and the PMOS. Also, we find the bipolar amplification of the PMOS. So we can use the laser and the simulation to find what's the reason. After this, according to the laser and the simulation analysis, we redesign the SRAM by modifying its bit cell. Here is the main change is the spacing between the sensitive load increase by 2.7 in an area efficient manner. So after this, having ion test shows that the SEU session, the AET of the new SRAM is greater than 37 MeV. So this uses the laser to position in the SEU sensitive load. The second example is do the further analysis of SEU induced backload. Here is the ADC. We do the experiment and we find the ADC with backload under heavy ion irradiation. Here is the microscope. We find the ESD transistor and the interconnection around it with burn. However, when we do the laser test, directly strike on the ESD transistor doesn't induce backload. Backload was found after the stroke on the capacitor in the ESD structure. Here is the circuit here. And we find when we strike the capacitor, the result will be the transistor will be backload. So the capacitor is the main reason to cause the high current and make the transistor backload. So it is impossible by the heavy ion to do this. So ion test is difficult to position a failure source when the failure load model and the source load are different. When we use the laser test, it can be do quite well. Finally, I was talking about the test method for distinguishing SEU and SET. Also, we will give some SET analysis. I think a lot of talk about the SET has become a serious problem because as the process technology advances, the ratio of the typical SET pass width and the typical circuit period increase, making SET easy to be captured by sequential cells. So here is the figure here. And also we find the ratio of the typical SET PW and the typical cell delay increase, making SET easier to propagate on logical paths. Here is the 65 nanometer test result. It's the SET and the at the unhardened DFF chain and also the SEU hardened DFT chain. We find for 65 unhardened circuit, SET surpass SEU and becomes the dominant area source. For 65 hardened circuit, SET is almost the only area source. We can see this is the figure on the right. So how to distinguish the SET and the SEU? So we should find a method to distinguishing the SET and the SEU. We know for the transition method, the SEU is record the total error after a certain fluence initiation. So the cross section just the error over the fluence. So when we plot the cross section with the LET, so we can find which one is the SET and which one is the SEU. Now here we describe a time domain test and analysis. We record the error every delta t during initiation. General delta t will be less than 0.1 second to make sure only one event happened during the delta t. We can plot the error accumulation with time for each type of ion. So SEU and SET can be distinguished by observing the time domain plot. Here is the transitional figure. And here is the time domain method. We can find here, all this one is the SET, okay. And when we see the figure, we can easily find which one is the SET and which one is SEU. So when we plot the in time domain, provide the insight to the detailed process of the error accumulation. And for the discrete jumping in the time domain curve, indicated the single event multi-cell upset. Single event on the global singular, such as clock and reset, can cause the SEMU as large as several thousand upset. So we can see this SET very clearly. Also, here is just some more detail for the SET at the 65 nanometers. So when we use the synchronous reset, we cannot see the SET. Use this one, we can do some for the hardness. Since we find here is DF dies, we will find that they do have some, this is the dies, and here is the DF dies. We find, use the DF dies, they cannot limit the SET. So we use the RDF dies. So dies is good for reduce the SEU, but nothing for the SET. Traditional SET hardening method is a delay field. It's useful for mitigate SEMU, but still sensitive to the SET. So redundant delay field remove SET completely. So this just means when we distinguish SET and SEU, we will find how to hardness the SET. So this is kind of the method for application. Time domain test and the analysis method give more information without additional bin time and cost. It helps better recognize and mitigate the SEU and the SET. finally, I think radiation assurance test is very interesting, but also very complicated. It always needs joint effort to find a better solution. And BMTI is looking forward to cooperation with related partners to do this. And thank you for your attention.